Hi, my name is Amber Lavasser, and I'm going to be talking to you today about all-electric HVAC systems. This video is provided as part of the Stanford Building Decarbonization Learning Accelerator, which was founded in 2021 to promote the teaching of building decarbonization in higher education. So first, as a reminder, how do we get to a decarbonized building? So from a typical building, we want to first reduce energy consumption as much as possible. Next, we electrify the building, and finally, we add renewables and batteries. And for a more in-depth look at this, please take a look at our introduction video or some of our other slide decks. This video will focus mostly on the all-electric building component. So first of all, as a reminder, how is gas currently being used in our HVAC systems? So this is a look at a typical residential gas furnace. So a lot of houses in the US, especially in the Northeast, have these kinds of furnaces. So it's using gas combustion to heat air, which is then distributed around the house. The efficiency can range on this and is particularly dependent on how old the equipment is, but somewhere in the neighborhood of 70 to 95%. A similar system is often used in commercial buildings where gas combustion heats hot water or maybe even creates steam, which is distributed around the building. Again, efficiency depends on age, but 70 to 85% is typical. So over the last 20 years or so, the renewable energy in the power grid has been increasing. So the carbon emissions of electric power have been going down and have reduced actually by about 26% between 2005 and 2018. But the carbon emissions from buildings themselves haven't changed. So we really haven't made much headway in eliminating the gas use in the buildings themselves. So how can we do that? So there's a number of electric space heating options, and we'll go through just a few of the common ones, but there's really a lot of different systems available. So this is probably the most typical, and you can already find this in a lot of houses, particularly in the Southeast, where we use electric resistance to heat. So that could come as just baseboard heaters that you'll see around your house. It could also be an electric furnace, which operates essentially the same as the gas furnace by distributing air throughout the house through ducts. But instead of using gas to heat that air, it actually uses electricity. Electric resistance can also be applied in a commercial setting, either as an electric resistance heater installed directly in a duct, or as an electric boiler. So an electric boiler would heat hot water, which is then distributed around the building. Electric resistance is 100% efficient, so all of the electricity is transferred into heat. The problem here is that electricity on a per unit basis is far more expensive than gas. So if you look at the example on the left for a gas boiler, it needs only slightly more gas to produce 100 units of heat, but it only costs $18 per MMBTU, whereas the same system with an electric resistance boiler would cost $57. So it's really a big price jump, and that's often why this technology isn't really applied, especially in markets like California with expensive electricity. But when is electric resistance an appropriate choice? So this is an example of a great building, the Rocky Mountain Institute Innovation Center in Basalt, Colorado. And in this building, they super insulated the building. So instead of using a typical maybe R10, they went all the way up to R40. And it's super efficiently designed so that the actual heat required is so small that it's fine to use electric resistance because it won't end up being a large bill since it's very rarely turned on. So this is an appropriate application for electric resistance heating, although it's not usually the best method. So the preferred method for electric heating is heat pumps, which is really what we'll dive into for the rest of the video. So why are heat pumps so much better? So as we saw, a natural gas boiler about 80% efficient, so 1 unit of gas in, 0.8 units of heat out. Electric resistance, again, 100% efficient, 1 in, 1 out. A heat pump, on the other hand, can be 300 to 500% efficient. So 1 kilowatt hour of electricity in can produce 3 to 5 kilowatt hours of heating. And how does that actually happen? So a heat pump just moves heat from one place to another instead of generating heat itself. So it uses the refrigeration cycle to pull heat from outdoors, and inject it into the building, which is why the efficiency can be better than 100%. So this efficiency for heat pumps, we don't usually refer to it as 300 to 500% efficient. We usually talk about it in terms of coefficient of performance, or COP. And the COP is just the energy out divided by the energy in. So in our previous example, an efficiency of 300% would be a COP of 3, which means 1 unit of electricity is able to produce 3 units of heat. And now when we compare the cost metrics of a heat pump to an electric boiler, because the heat pump only needs a third as much electricity as the boiler, the cost, of course, is much lower. So now we're down to only $19 per MMBTU of heat, as compared to $57 for the electric boiler. And as a reminder, the gas boiler was $18, so the price is very comparable. And in the coming years, we're expecting gas prices to increase, and likely very soon the heat pump will actually be less expensive to operate. So how are heat pumps actually being applied in buildings? So we'll look at a few different examples of different technologies and how they can be used. So first of all, this is probably the most common application, an air source heat pump. So that means it's moving heat from the outdoor air into the airstream of a building, or the water stream of a building. So this one on the left is just an air source heat pump that heats and cools the air directly and distributes throughout the building through ducts. On the right is an air source heat pump that's able to create hot or cold water, which is then distributed up throughout the building through pipes. Air source heat pumps also used in residential applications. This is a slightly different application. So the outdoor unit and the indoor unit are both components of the heat pump, where the outdoor unit is able to reject heat outdoors or pull heat from the outdoors, which heats up refrigerant. The refrigerant is then piped to the indoor unit, where it's able to heat or cool the indoor space. The central system is a similar application, but instead of having a small single indoor unit mounted on a wall like you see on the left, this is a more typical central air handler, which is distributing hot or cold air throughout ducts. Split systems can actually be used in commercial applications as well, typically when there's one single room that has a large cooling load, like an IDF room where there's large server banks that need a lot of cooling, but the surrounding areas don't need the same amount of cooling. So that is a common application of a split system. Packaged terminal heat pumps, or PTHPs, are very common in hotels. So this picture is actually a hotel setting where each room needs individual controls. So they actually are installed directly through an exterior wall. So in the same unit, they're able to reject heat or pull heat from outdoors and expel it into the room without any need for ductwork or piping or anything. Variable refrigerant flow systems are very common and getting more popular because it's an all-in-one solution. So the outdoor units are essentially operate as air source heat pumps, similar to the split system. But instead of having a single outdoor unit and a single indoor unit, a larger outdoor unit or many outdoor units paired together are connected with a whole array of indoor units throughout a building. So this diagram shows 8 indoor units. There can be many more. The big benefits of VRF is that the outdoor unit and indoor units are connected by refrigerant piping, which is relatively small. And they're able to simultaneously heat and cool different zones in the same building. This is just a look at some different options. So VRF units are really customizable. You can pick from a whole different array of indoor units. This is just a few examples that can be integrated into an existing building or a new building. They're pretty easy to tuck away. Like that example you see with the staircase where it's hidden entirely in a box, so it integrates well in a historic building. The outdoor units are much larger, but typically not as large as an air source heat pump, and they can be located on the roof of the building or outdoors adjacent to the building. The next option for heat pumps is a water source heat pump. So these are commonly ground paired, so sometimes referred to as geothermal, but more technically correct is ground source heat pump. So these have entire loops of water, usually mixed with a small amount of refrigerant or antifreeze. which circulates throughout the ground, and the ground is actually used as a heat source or a heat sink. So heat from the building is either pumped into the ground or extracted from the ground, and it can be stored seasonally. So if a building is being cooled all summer, the ground heats up, and then in the winter, when it switches to heating mode, it then pulls that heat out of the ground and puts it back into the building. So this is a really effective and efficient system, particularly in climates with big swings, so very hot summers and very cold winters. Heat recovery chillers are capable of creating hot water and chilled water, and can have some great efficiency benefits in situations where both hot water and chilled water are often required simultaneously. So one of the best applications for these is utility plants. So the Stanford Central Energy Facility is a great example of how these can be applied. So they have a whole bank of heat recovery chillers, so making chilled and hot water for the entire university campus. And because there's such an array of different buildings and different uses, they need hot water and chilled water both at almost all times. So this really has efficiency benefits, and you can see that when Stanford transitioned to this new plant, their peak energy and emissions reduced by 50%. And with the addition of renewable energy, they're very close to entirely carbon-free campus. So thank you so much for listening. I hope this gives you a good introduction to heat pump systems. And if you'd like to learn more, please take a look at our many slide decks, exercises, case studies. And thank you so much.